Okay, so this is the second part of the lectures about the sequential organization of behavior and processes. Last week in the first, I talked a little bit about the general problem of generating sequential sequences of behaviors or sequences of mental acts. And I talked about it from the perspective of dynamic field theory, where any kind of behavior or mental state is represented by a stable state of neural activation, a peak in various fields, for instance. So attractor state. And as attractors, they resist change, right? That's the very property of stability. And therefore, understanding how you generate sequences first means understanding how you can make an attractor disappear, make it unstable, which means you're inducing an instability, making the stability go away. And I went through an example that showed how that works, and that was based on the concept of the condition of satisfaction that I'm reminding you of here. So the notion is that they're always paired units. So here in this example, I have a single node, or I have a whole field. The field, you could think of that as, fields of various dimensions. 0 dimension is a node, and 1, 2, 3, 4 dimensions would be more than that. And you know already from the earlier lectures that you could have ensembles of fields that are bound through space. That we call those intentional fields, in the sense they represent what currently controls action or thought. So what is your intention, what you want to bring about? And if they are fields, they are attached with contents. That is, they can represent one of many possible thoughts. Or, for instance, a visual location that you're looking for, a particular cue. Looking in visual search, like you're looking for an object of a particular kind, and the location within the corresponding field would be the specifying that action. And generically, the idea is, these intention fields are excitatory in nature. That is, they can bring about stuff. Downstream neurons are impacted on them. So if downstream you have some action systems, maybe with their own sensory inputs, you can do things that bring about what you're intending to do. And then the notion is that the intention state predicts the outcome. That is, that there is some connectivity that says, or that is organized such that the perceptual or internal representation of what a successful action could be is encoded in some neural connectivity, so that in another field that we call a condition of satisfaction field, there is pre-activation, not yet at a peak, but some priming input to that field that sets up that field to build a peak at the location that matches that prediction. So in a zero-dimension case, the only prediction is that you're lifting that condition of satisfaction node closer to threshold, because the corresponding intention is going on. While in actual fields, you can have contents. You can, in the example I showed you, the system was seeking colored objects, and the prediction is that if you're looking for a blue object, you're going to see a blue object, and it was a particular input at the blue, for instance, in this case, blue dimension, a location in the field that primes this system build a peak at that location. And then the idea is that the conditional satisfaction system goes through detection, that is, creates a peak or turns on the node if input it receives from the sensory surface, could also be from other parts of the neural architecture, matches that prediction, so that the spatial overlap between predictive input and this actual input leads to a detection instability. And that detection instability turns on the condition of satisfaction, which then inhibits the original intention. So the intention could be in the field level or the node level. This little full filled circle here is sort of a symbol for inhibitory projection. So this is an inhibitory neuron. And when that inhibition, I think that's, when that inhibition is effective, it pushes the activation here through the reverse detection instability. So the node is deactivated or the peak disappears. As a result, it doesn't have that excitatory input anymore, the predictive input to the conditional satisfaction node, and things are arranged such that the peak here in this field can only be sustained if there is this input and the prediction. So this field also goes through reverse detection instability. And then when it does that, the inhibition falls away and this node remains, the conditional satisfaction is also off, and then this entire system is off. So this intention, whatever it is done and no longer affecting downstream systems. There is a little bit of an inconsistency here because I'm saying this is an inhibitory system. As an inhibitory system, it can't actually go through a detection instability per se. It's not, it doesn't have this excitatory interaction to go through a detection instability. And so in reality, the detection instability must occur somewhere in the perceptual pathway. And so this system does pure inhibition. We sometimes use actual fields as conditional satisfaction fields, which really is just a simplification that rather than have this extra perceptual system that represents the signal, we do that in this field. The actual mathematics of this system, where this is really treated just like an inhibitory variable, is in this graph. This is the graph that I got a little bit confused talking about last time. It didn't put it into the video that's online. The graph actually was right. I was just confused. This is an illustration of the dynamics of the condition of satisfaction, of this mechanism of deactivating a state. Oops, that uses sort of the Amari way of analyzing the dynamics. So here on the horizontal axis, you have the neuron that represents the intention. That's an excitatory neuron. And on the vertical axis, you have the neuron that represents the condition of satisfaction. That will be an inhibitory neuron. You saw these kind of phase diagrams for combinations of excitatory and inhibitory in Amari's paper at some point when you did an exercise early on, or we also in the exercise actually discussed the piecewise linear analysis of dynamics like that. And that's what I'm alluding to here. These numbers characterize the quadrants of this system. So number one is this positive quadrant, so where both excitation and inhibition is positive. Number two is where only inhibition is positive, excitation negative. Number three here in the middle, this is this area here where both are negative. This is the off state. And number four is when there's only excitation, no inhibition. Number four here. And what I'm showing here with these circles are the fixed points that are attractors of dynamics approximated here as piecewise linear dynamics with a step function threshold. So in the generic Amari, two-layer Amari dynamics that we're using in dynamic field theory. So this here would be, for instance, the fixed point that is valid for any initial condition here in quadrant number one. So any initial condition here would move in the direction of that attractor here, attractor one. Of course, as soon as it leaves quadrant number one, this is no longer valid. When it's in quadrant number two, it would be moving toward this attractor right down here. So, and so on. And some of you might have used this kind of visualization to understand how oscillations come about. Those come about in situations in which the attractive fixed point always lies in the next quadrant, and then the system sort of chases around a circle. Now, the way the condition of satisfaction works is illustrated here by these different colors. The default setting is the blue setting. So in the blue setting, as you're seeing, the system is actually bistable. It can stability is always achieved when the attractive fixed point is in the same quadrant to which it pertains. So for instance, if in quadrant number three, there is a fixed point in the same quadrant, then activation states will in fact converge on this fixed point. The system will be sitting here. So if you start anywhere here in quadrant number three, you will be going to this attractor, and that is the off state. So this there's no activation, no inhibition, so you're below threshold, off. On the other hand, here in quadrant number four, in the blue case, there's also an attractor. So any condition in here will be converging on this fixed point, and that's when this the intention is on. the excited state is positive and is no significant inhibition. So this is when system is working. So what you do when you start a behavior is you set the system into this attractor. And you do that by giving some boost to excitatory boost to the intentional unit. That means shifting everything to the right, right? There will be an excited boost, and you have to shift it enough for this attractor to move into the fourth quadrant. So in the third quadrant, there's no longer a stable fixed point system, will be moving off into the fourth quadrant. Once it's here, it would actually be moving then here to the actual attractor. If you turn off that signal that sets the intention at some point while it's relaxing here, the attractor would be moving here, so that exploits the bistability. So once you've set it, it stays on. So you only need to give it a brief impulse to set it. That's how we typically set working memories. So while it is sitting in this attractor 4, it is doing the behavior, whatever it is. In the example I showed you, the vehicle is moving around, searching for the color. So that can take variable amounts of time, and the system is in a stable state, and that makes it possible to sustain all that time. Now, the condition of satisfaction signal comes, from somewhere, sensory path or some other inputs, and that's the signal that shifts the dynamics, adds inhibition, so it shifts the dynamics upwards. So the green line would, the green symbols reflect that state when the inhibition inhibition has been added, and so what you arrange things such that when that inhibition arises, the attractor 4 moves into the first quadrant, so it's no longer an attractor. The system would be crossing over into the first quadrant where inhibition arises. As it enters it, it moves into the toward the attractor. The arrow actually should be a little less inclined because it should be moving toward number 1 here, or I should have plotted the whole thing a little bit higher. So it's moving into this quadrant and then off toward the attractor 4 quadrant number 1 this year. And as it enters quadrant number 2, it moves toward the attractor for number 2. And as it enters quadrant 3, it would be moving toward the fixed point for 3, and that's an attractor. So it would actually come to rest here, and that's again an off state. The system would have turned itself off. But rather than go directly from 4 to 3, it went around this way, and this way it goes around is dictated by the excitatory inhibitory coupling of the two-layer Amari system. That's called an active transient, according to Amari. It creates a time course that is sort of like the limit cycle, the periodic solution, except it stops. If 3 was again here in this quadrant, then you would actually get the oscillation going. But because 3 is in its own quadrant, it stops. You see, this is not yet the blue situation because I have assumed that the signal that signals the condition of satisfaction hasn't gone away yet. That would, of course, happen in the example with the vehicle. As the vehicle is no longer looking for or stabilizing the color it desires, it will start to move away from that color, and at that point that sensory input would go away, and then it would be falling back into its default position initially. So this is the fundamental mechanism of the active transient. It is sort of the mathematical analysis that is true for all the different uses of the condition of satisfaction. It's actually not something we've published very clearly, and we've been planning to do that for a long time now. It's, why do we need that active transient? Essentially, we need some finite amount of time, a well-defined amount of time during which this transition takes place and is no longer disturbed by anything else happening at the same time. And that's important in a practical sense. So let's say you're sitting here, you're really doing your intention, and now you start to get the signal that that says you're done. Why not arrange this so that the system goes directly here, just go directly, suppress this directly without having this self-excitatory, the Amari dynamics, which has self-excitation and has this driving of the inhibition from the excitation. we've actually played with ideas like that and tried to simplify things this way. Like, for instance, the sensory signal itself is directly inhibitory, makes a negative input into equation. We don't need an inhibitory variable, let's say. You just directly inhibitory would mean you directly move this here to the left. The problem that arises is that if you do that, then the activation in your intentional variable would go away, and it's not untypical that as it goes away, the signal that drives your inhibition also goes away. And as it goes away, you no longer receive that inhibition, and then you go back to activation. And so you can get some kind of self-termination of that switching off. Here, that will not happen in the sense that the system just goes this path. Once you've pushed it here above this, it takes its path, and it doesn't really matter at which point you turn off that external signal that drives the inhibition. So as it is moving up here, it is still excited. It is still doing whatever action it's doing, and therefore still keeping the condition of satisfaction signal going. And that's turned out to be a very useful concept. It's actually, in a sense, also a much broader concept, because we are generating active behavior by oscillatory states. I haven't expanded this in this lecture. In the summer semester, I teach about motor control, where that happens, where time courses are generated as limit cycles. So periodic solutions, self-generated neural activation. And this is, in a sense, the simplest case of that. So it's a mental act of generating a time course, which means the time course of turning off, which is also sort of the unit of how you make an autonomous mental move, let's say, in a more general sense. That's all I want to say about the mathematics of this. So this is just an intermediate conclusion, just saying this is how the condition of satisfaction organizes the transition away from a current stable state that would be a behavioral or a mental state. And for that, it needs some signal. And I always now refer to, in the example I used last week, I showed explicit an example where it comes from a sensor. The signal that drives the condition of satisfaction comes from the world, from a sensor. But more generally, it can be also some neural state when you have a pure mental process. And I showed you this example of mental mapping, where you're doing everything just in your mind. And in that case, the signal that marks that you're done, for instance, in this case, done would mean that you have created a peak in the mental map. Then it is a peak detector, so a particular coupling coming from that field that detects a peak has been formed, that would provide that signal that creates the condition of satisfaction, which then inhibits the process that currently, for instance, drives the relational field to create an instance, and then you can go off to do the next thing. So this is about how behavior can sort of turn itself off based on an external or an internal signal, and the architecture needs to know what signal that is. What would be the condition of satisfaction, really, in the philosophical sense? It doesn't actually say yet what to do then, right? What is the next thing that you're going to do? When you think about sequences, it has these two components. First, you got to finish what you're doing now, and then you have to select the next thing that you do. That next thing depends on the neural architecture, the whole system that you have. And I want to discuss here three concepts that are in the literature, sort of the agreement in the literature that these are the three ways of how serial order, sequential steps that are whose order would be reproducible or have some regularity in the nervous system. The three ways how serial order could be organized, and there is some evidence for each of those, some neural evidence, some behavioral evidence. So it is likely that in the nervous system, these three systems are used in different places. And in fact, in our theory, dynamical field theory, we're using the three systems as well in different places. And I'll point that out to you. This is from a review article by Helzer and Burgess. It's quite old, more than 20 years old, but it is still quite relevant. It's a good article if you want to read it. Easily find that if you Google it. And so these three concepts are called gradient-based chaining and positional systems for serial order. They are described in this paper and in the literature in a bit more specific way than I will describe them now. They stand for somehow much more general principles, one could say, but they're also, they capture the core of those principles. Now, I'll discuss them in this order. So the gradient-based system essentially says that if you have different neural populations here, this is a model from the Grossberg group with someone with whom we actually collaborated here. The Kazaronian was a doctoral student, did this in his doctoral dissertation, and then later he was in Lugano with Schmidhuber and worked with us in a European project. And we've used ideas from his thesis in that project. I'll not explain the more advanced work we did, but this is from his thesis work. And it's just one example of using that principle. So here, these X are neurons or neural populations, actually have more complex structure that I won't explain in detail. And the notion is that these neurons are at different levels of activation. This bar shows up the different levels of activation. And you would encode the temporal order in which these neurons receive their input, or in which you want them to become activated, encode that into this level of activation that they have. So one difficulty with really doing it that way is that you would have to keep a neuron firing at different levels of activation as a sort of working memory, that is, keep it firing even after its input is gone. This is sometimes called the line attractor picture, and it is sort of like what the field does. In the field, the peak is a particular location, and it is a working memory of the location. If the peak is sustained, it is no longer dependent on inputs to keep that information around at which level it is. That's the standard model for working memory. For working memory of some low dimensional thing. So we call that magic working memory, right? We talked about that. So for space, for colors, for features, and so on. Or for actions, characterized by parameters. So that works in low dimensional spaces. And so an alternative is that you would keep a neuron firing at a particular level, and that level encodes the metric information. So that will be rate code. This idea is around, is some discussion whether it is real in the nervous system. It's not, I would say, not entirely clear, but there are proposals how to do that. Particular circuits, it's essentially something in which the minus U term in the neural dynamics that turns the activation, makes it go to the resting state, that you compensate for that minus U term by adding a plus U term. So you have a sigmoid that is approximately linear, have some self-excitation that is approximately linear. It could sort of cancel the minus U term. If you cancel the minus U term, you have an equation that U dot equals 0. So that will be constant firing. And then you could shift it up and around. You can see it's a precarious thing, and I could wonder how well that works in general, but this is a demonstration here, this paper by Kazaronian, that shows how it could be used in principle. So here in this case, what you see is that when the inputs are presented in particular order, then the first neuron ends up in a higher activation state than the second, than the third, even though their parameter values are identical. It's just a question of their the order in which they were activated. And it's this connection among neighboring units that makes that once a neighboring neuron is activated, it will not allow the next neighbor to reach the same level. And then once two are activated, they don't allow the next unit to become activated at a further level. Somewhat specific, right? But it's thinkable to do it that way. So that's the difficulty with actually using serial order, is using the gradient picture for some arbitrary order. Here, this is a demonstration that just changing the order, you can encode the order in these levels of activation, with some question about how robust a mechanism like that is. What is much more generic is, however, is that if you have some difference in activation, you could now select the highest level of activation as the next item. and that's what we've been doing a lot. I haven't explained it, because you could say, if you just arrange for these units to make input into a field, for instance, or some competitive network of nodes, then once you make these nodes, boost them to make a detection decision, and they have different levels of input, the one with most input will win, right? That's just normal selective competitive selection. So it's very generic that you could just pick out the next item by bringing a field or a population of competing neurons to the detection threshold, and then the winner will come up. That will be the next item that comes up. So that's, for instance, that in the model of visual search that I showed you 1 or 2 lectures ago, that's how it actually worked there. The location with most input won. And that is also true in the relational field in the mental mapping model. It was exactly that mechanism, that the location with most input creates the peak that is then put into the mental model, and so on. And so the only thing that you need for that to generate, that's selecting the next item, and then you have to have the same mechanism we just discussed, the condition of satisfaction, how that peak would be eliminated, and then you would do the next choice, and so on. Of course, to achieve then still some meaningful sequence, you would have to have some way of how to act back onto this level at which competition takes place. In the visual search case, well, it was the salience map, or whatever. Like you could think of a mental space where you have all your hypotheses, what you might want to say, and now you pick the most salient thing. You really said idiot, or even a worse word, because you were in the car and were excited about some stupid driver. You said that word, and now you can get rid of the activation and want to say the next word. If you don't do something special, you will say idiot again, idiot, because maybe it's the most salient word right now in your mental map. So to make more complex sequences, you'd have to have some way of how that peak, that large input at the location, let's say this is the node for idiot, goes away, so that you have a chance to select the next one. And that's what in our models was this inhibition of return. There is some notion of inhibition of return in the literature, which is, again, observed in slightly different situations. So we and a number of other models have sort of taken this idea and generalized it, even though the evidence for it is quite narrow. And it's an idea that where you had a peak, you have built also an inhibitory representation, and that inhibitory representation then lowers the inputs in the salience map, and then you the next most activated location has a chance to get selected. That inhibition is a signature of actually memory. That is, you have to have working memory for where you looked, and there is evidence that you do have that in many cases. It's only it's limited capacity, so you only inhibit things that you have put into your visual foreground, for instance, like up to 4 approximately. So after some time, you will be reactivating items that you looked at before. And that is true in visual search concretely. You do look back at the items that you've looked at before, attend to items, and actually happens in other kind of mental activities. So it is quite possible that that is as powerful as that mechanism is. It's not, doesn't prevent you from revisiting the same choices over and over again. Perseveration actually is something studied as a signature of such a failure to inhibit longer term. So gradient-based selection is generic. It's very common, and it's very common in our models, very common in other models, that neural network models that are sort of like dirty dynamical field, not mathematically so well characterized dynamical field models, really. Whether it is used to encode serial order is maybe a little bit less clear. Okay, in some of our models, I just wanted to say how you generalize that. So if you think of the units of representation being these units, intention, condition of satisfaction nodes, you could also say they are just generically these excitatory inhibitory pairs that we think are sort of the units of representation in neural terms, so that they all have this property of being self-terminating, then you could have a lot of systems that are always competing, and which one is activated would always be a question of the current, how well they match the current situation, for instance, current sensory stimulation or in some mental representation, and so we would understand how one of those choices goes off, and then which one is activated next would again depend on that language. Okay, now chaining. Chaining is a much more specific idea. Would be the idea that one neuron activated, and then when that neuron gets deactivated, it's always then the next one it projects onto. I didn't put that diagram back here, but it would be this sort of idea that after neuron 1 comes neuron 2, after neuron 2 comes neuron 3. Actually, there is already here a branch. I'll come to that. There's some difficulty with that, but it's a very straightforward kind of idea. And they have lots of models in the literature that are like that. They are considered reasonable models for fixed action patterns. So you do have, especially in the neural periphery, you have patterns like that. For instance, very well studied in invertebrates, that the footfall pattern that you have in locomotory patterns are sometimes effectively set up like that. That is, there is some activation for one muscle that drives one particular phase of a leg movement, and then that muscle inhibits a subsequent, a muscle that is involved in the next phase. And when that muscle falls silent, when you're done, the next muscle is released from inhibition, and then it goes on. And you could think more macroscopically that fixed action patterns that you've learned, for instance, the fact that when you reach, you open your hand and then close your hand, you could think of that as being fixed. That is, this, you're never going to reverse that order. It's a fixed order, and you could then wire it up that way. And so that's a common idea, that there would be some fixed patterns that could be encoded in that way. I'll point to you later how that could be learned. So you encountered that in our in early models where I didn't explain it very well. We have essentially embraced this metaphor that is very common in the nervous system. Actually, suppose the basal ganglia are viewed as being organized like that as globally, but you also see it really in the periphery of the nervous system in many different animals. This is this double inhibition. We call these preconditioned nodes. So this would be a node that when it's active, it inhibits this intention. Similarly, this node would inhibit that intention. So these two intentions, for instance, cannot go on while this preconditioned node is activated. It would be in working memory, let's say, to be activated. And then you could arrange for some other behaviors like this one, inhibiting this node through its condition of satisfaction. See, the condition of satisfaction is inhibitory in nature, so it should have an inhibitory effect, and maybe that's the logic of how this double inhibition comes about. So this condition of satisfaction would inhibit the preconditioned node, and that would release from inhibition that intention node. So if there's some other input to that intention node, it could then come on, just as this inhibition node falls away. So that would be a concrete way how chaining could be arranged. And of course, there could be other neural diagrams where you could have this excite that, but it's not yet enough, and then you have that in addition, and so on. So you could have some particular multiple ways of doing that. But this double inhibition is actually considered to be neurally realistic, which also, well, I'll come back to that. So it's been discussed in the literature as a model of serial order. As a general approach, you could see it is not so convincing in the sense that if you have, it means that the connectivity is encoding the order, and therefore, if you have a unit that's active, it should uniquely determine a successor. So it would be very difficult to say I have a serial order in which after, let's say, the number 3 comes the number 2 in one phone number, but later in the phone number is another 3, and after that 3 comes 7, right? And then this wouldn't work, unlike that diagram that I hinted at. there are fixes for that. You could have multiple copies of 3, and then there would be the 3 that's followed by 5 and 3 that's followed by something else. But you see that that begs the question where that comes from. And then you're actually not doing pure chaining. Then you actually have some positional coding where there are different kinds of 3 context units and so on. There's some stories that things like that might exist. People look at birdsong, for instance, as an example, where you do these very intricate sequences. The different songs are characterized by their order of different tones, and there's some proposal that you would have some material to work with. But let's not go too deep into that. So it's not so clear that that's very flexible. It is probably something that is emerges from practice, that fixed patterns are like that. And I'll show you in a moment how it could emerge from such patterns. So the most general idea is positional representation. It's the most generic one that uses the principle of space code that dynamical field theory uses. It's actually the principle also in a localist sense. The first uses rate code, right? The gradient picture. This uses space code. So the idea here is that you would have some fixed neural circuitry that sets up the sequential activation. But what the contents is of the different steps that you do, that would be learned by projection onto other neurons. So that what the neuron stands for in the space code sense would be fixed by its neural connectivity. So here, the example that I showed you in last lectures, the actual architecture underlying it was a system like that. So up here are these nodes whose connectivity implements sequential activation. For instance, this unit, every unit here along this line has a memory unit attached to it. So when this new unit is active, it drives this unit into the activated state that's bistable. So even as that unit becomes unstable, this unit remains stable. For instance, the unit that's currently active and its memory node is active, while all the others are off. And then there's some excitatory projection. So that's a particular way of doing that. Excitatory projection, where this memory unit pre-activates the successor unit, but not enough to activate it. And that's all. And all of these units here at the bottom are bistable, but they will be inhibited by a condition of satisfaction. So here's an inhibitory unit. So from some lower level system here, there will be a signal that says we're done with whatever was the current state. This will wipe out inhibition excitation here. It will not wipe out the working memories. And so when you're then releasing from that inhibition by self-termination, right, the units come back up. And the one that will have a competitive advantage is the one that has a working memory just behind it. So this one will be coming up. And so in that sense, this is one particular way of how to set these up as a fixed order. And you see the preconditioned node would be another way of how to do that. So you could set up a network here that will, by pulsed condition of satisfaction input, will always switch to the next node, but it will be able to stay in one state for arbitrary amounts of time. Now, so we call these ordinal nodes in the sense that they represent the serial order. So this would be the first thing to do, the second, the third, and so on. The idea is what is done is encoded by neural projection in the usual way. So projecting onto some feature space. So here in this example, this is a feature space. In the robotic example, this was color. And so there's some learned, actually by Hebbian learning, you learn the connectivity between a node and what the color is that you're looking for at this moment, or what the feature value is. For instance, this node, let's say, stands for this region, and that node stands for this region, and so on. So you could have some arbitrary mapping, and this is how you could have the same. For instance, two nodes could both point to red, let's say, this node and that node. It doesn't matter at all. It doesn't matter for the sequential operation that they point to the same content. So the contents is separate from the ordinal structure. And so below that, you would have to have a machinery in which, again, the contents is connected to its condition of satisfaction. So the content must pre-activate the condition of satisfaction, and the condition of satisfaction must be inhibiting the system. And the important point is, in the case like this, the mechanism of switching should not depend on the contents. That is, you don't need a specific signal to say it's unit number 2 that I want to deactivate it, because that would mean that you have at more than one place the contents. So here only in this connectivity is the contents. You don't need to know the contents anywhere else. I mean, this projection, what's the condition of satisfaction? It's just a question of the properties of the space. For instance, if you're looking for color, then it's clear that the satisfaction is if you get a signal of the corresponding color, or it could be some other mapping. But that mapping would not be dependent on where in the sequence you encounter that contents. That's a pure question of contents. But the mechanism of how to make the sequence advance is only informed about a condition of satisfaction has been activated and not which one. And therefore, for instance, it just globally inhibits the system here, and then the system switches to the next stage, and that's a legitimate mechanism. If you do that with the double inhibition, you can design a corresponding system that will also have that property, that the signal that you need to switch doesn't need to know which node is currently active. So in the robotic example, there is, the intentional field, we call that action field then, is the thing that has projections onto the motor system. It actually also is in a closed loop because there can be perceptual activation coming from the motor system. For instance, when you actually do the tracking, the peak will reflect the precise color of what you're currently tracking, while there is a separate perception system for the conditional satisfaction. I wanted to show you a few examples. This is the example that I showed you last week. I didn't put in the same slides again that illustrate the vehicle driving to colors. I'm assuming you all remember that. And so this is just some highlights from that example. So here is the current representation of the intention, and it's a representation in a dynamic field over color, right? So for instance, you're looking for a particular color at this point in time, and the corresponding, or let's say that's the first color you're looking for. So the ordinal node number 1 is on because you're looking for that. And this is the field for the condition of satisfaction over color. And so it has this yellow input here is like below threshold, but more than background. So there's a little bit pre-activation at that location of that encodes the hue of the color that you're currently looking for. And then assuming at some point the vehicle does encounter an object of that kind that provides now enough localized input to push this peak above the detection instability. So here a peak has formed. See, this is positive, and you see it inhibits everything else in the field. As that condition of satisfaction acts, it inhibits the entire system. So you see all the ordinal nodes are suppressed, including the one that you just currently looked at. You see that the next ordinal nodes, the dashed line is the one that represents the next order to the red line. It's a little higher than everyone else because the memory node that corresponds to this first item is set, and that boosts that a little bit. That's why this one is different from everyone else. As the condition of satisfaction is stable, it inhibits the intention, so it deletes this peak here. The input to this field, actually, sorry, no, it's not right. It just deletes the serial nodes, but because the serial nodes go off, maybe red line goes off, it no longer provides this localized input to this field. The peak here goes away. As that peak goes away, so here it goes, it's gone. It's gone here. No longer gives the predictive input to this, the local input here goes away. This makes this peak go away. And when this peak goes away, it no longer has this inhibitory influence on the ordinal system, and the system is pushed back up. And now the node that has the competitive advantage and can suppress the other nodes is the one that was a little bit boosted by the memory. So it's the next one. Oops, sorry. That node apparently has neural connections to this color, and the system starts to look for that color. And as it builds a peak here, a condition of satisfaction peak arises. It's some sub-threshold input in the condition of satisfaction field that sets the system up for the next thing while this one here fades. So that now the system is ready to do the next act. That's how the transition works concretely in this system. Here is an even more detailed view. So this is what happens during learning. You're showing the robot this color. It has in some way been started by boosting the initial system. So it knows this is the color number 1, the first node is on. This peak here comes about because you have that input. And so it's in this phase that the system is actually learning this connectivity by Hebbian learning. There's an actual Hebbian rule where the activation of this node and the activation, this local region that's activated, they are strengthened. Those synaptic strengths are strengthened. And as the peak, the mapping from condition of satisfaction, from color to condition of satisfaction is not learned here, is fixed, assumed, given. So the system knows what the condition of satisfaction is. And what happens in this system is, as this peak is large enough, it excites the condition of satisfaction enough, which triggers this, that resets the ordinal nodes. They go away, you see. And the next one here is a little activated because it received that memory input from the memory unit connected to that. So when you move this here away, there is no more input. This here goes away, and then the next node comes up, and it's now you're presenting this, and now it learns that connection, and the same thing will happen. You see, the triggering was that so here in this system, the input is to the intention field. So this input here is used for learning. As that input to the intention field, that's later the input is, it's going to be the opposite. Later the learn connection puts the peak here, and while here it's the input that puts the peak here, and then you learn the connection. So this is an example from that work where this is the training period where Julia was presenting the system with different colors, and initially the first node was on in that interval, and the color was presented was this particular color. And it was in this period that the synaptic mechanism learned the connections to that color. And then you see the second item was on, this color was learned, the third item, that color, the fourth, that color. And the fifth, I believe, see, it's the same color again. This was some kind of proof to show that you can do that. While this is the action phase, in the action phase, the system is started here by a boost, and then the first node is on, and now it's on until its condition of satisfaction is met. So this transition from looking for this color to deactivating this peak, bring up the next node, and then the next color that's associated with that, that's what I just showed you. That's that transition. And I found the other colors. And here you see this feature that it's not a rhythmic activity. It can sustain variable amounts of time before it terminates its behavior as the robot moves around that arena. It is not having to go through the serial order in a fixed temporal pattern as many other models sustain. This looks regular just because Julia, who was training that system, was doing this somewhat predictable timing, but you see, not perfectly. Like this takes a little longer and others take shorter. This is showing the relationship between the condition of satisfaction and the intentional. I just showed this amplified. This is the survey over the whole thing. And this is another view of that where you see the concrete colors, and it's just to point out that the blue appears twice here in training, and then it's also able to do that twice in acting it out. And it doesn't have any difficulty with that. You see that, you actually see how this is where in the field a color matching object is seen. During training, it's always sort of shown in the same spot, and during the actual action, the system picks up the object first somewhere, and then it actually orients to the object, as you might have remembered from the videos, and then that's when the object looms large on its retinal array. Okay, so this positional representation is very flexible, very general. We use it exactly for that, for very flexible general kinds of ideas. I want 2 points about that. First of all, it is a chaining system if you just look at the ordinal nodes, right? The ordinal nodes are chained. And so you could see that if you just have learned fixed projections, then that unit itself is a chaining unit, right? So from the positional system, you could get chaining. Just if you think of one particular ordinal system, becoming specialized in just one particular action. Well, the one challenge with this picture is that you would have to have some way of how these ordinal units are connected with enough stuff so that they can learn anything. Because we're not talking about synapses growing out of nowhere. For this to happen, especially to happen on the short time scale of a single demonstration or simple experience, it would have to use synapses that exist, so just tune them up. And that would mean that you are looking at a population here, if you take literally as a model, that has potential connectivity to whatever field is required to learn over. So does that exist? Well, there actually is one of the thoughts, but this is like a very vague qualitative kind of thought, that hippocampus plays a role like that. So hippocampus is connected to a lot of different sensory and motor domains. So it has that potential to project to many different parts of the brain. So it could potentially provide a substrate for these kind of systems and connecting to all these. There's some exciting work that actually my colleague San Cheng here in Bochum is working on. Oh, I had some problem here. So again, okay, I'm back. That actually hippocampus could play that role. And there's a bizarre effect. As you might know, in hippocampus, sequences are sometimes observed in terms of sequences of motor behaviors, like a rat is going around a labyrinth or in some particular way in an arena, and then you have some encoding of space, and then you find so-called replay, that is, the rat might be even during sleep or while resting, you might see activation patterns in the brain that match the activation patterns when he was doing that locomotion, as if it was mentally rehearsing that sequence. Bizarrely, it sometimes goes backwards, rehearsing the path, but backwards. Now, that's called replay. And there's kind of speculation that it's like consolidating the memories. The bizarre observation that is a starting point for this kind of thought is that there's also what is called preplay. That is, sometimes you see a certain sequence of neural events that occur before the rat has had a chance to explore that labyrinth. And then when it explores that and does a certain sequence, these neural populations that you recorded from, you're fixed by the electrodes that you have, start to be associated with different locations. Place fields form, as that's called. And so then you can interpret what that spatially means, but it looks like the sequential activation can be generated even before the neurons come to stand for a particular location. So that would be an idea that this sort of structure exists in hippocampus, and that when the animal learns a place representation, it actually just learns these projections. Now, that's just a story I'm telling, and it was going to be a whole project or more than one project to see if something like that could be real. People talk about the spatial dimension of hippocampal neurophysiology as being just a placeholder for a general indexing function, that locations there could be pointing to things, and that would be one idea, that they could be working that way. Again, this is far from clear that that's exactly how it's done, and dynamic field theory does not actually claim that our units are necessarily localized in the brain and so on. So it's a general issue, but it is a practical issue to, if you think about neural field architectures, to have these projections, that you have to assume that there are many ordinal systems in different places that can project, because it's not trivial to be able to connect just about anything. So we're certainly postulating that there are many copies of these ordinal systems. Okay, now I want to end this unit about sequential order with an example that we just recently published. Is sort of like Julia Zanemiska's doctoral thesis redone in a scenario that is less artificial in a sense. And I showed that also because it is an example of an architecture that has this universal structure of dynamical field theory. You know, we have this idea that embodied cognition, sensory motor, grounding of cognition, and so all forms of cognition are ultimately anchored in some perception and in some action. And so you have a whole sub-architecture here that is about scene representation and attention, and a whole architecture that's about bringing about movement that are directed at objects that you attend to. Now, I'm not going to explain those in detail, but you are familiar with a lot of that. So if you look in here, you recognize stuff that we've seen before. For instance, the scene memory, where you would be able to put items into particular locations by specifying feature values, again, colors. You have a way of selecting from that a memory location. You have a mechanism for visual search, for knowing where in the scene which color is. As a salience map that could select, do spatial attentional selection, and so on. Plus some circuitry, how to control that I'm not going to explain precisely. There's some special stuff. For instance, there is an offset detector that notices that something that was visible suddenly turns away, a transient detector essentially. See in a moment that plays a role. I haven't explained as much the movement system. In the summer semester, we're dealing with some of aspects of that, but not with all. So what you have here is a representation of target that actually takes information from the scene representation, combines it with current sensory information, and then selects a target location. It has a representation of where the end effector, the hand, is at a particular moment in time, centers those. So it does a coordinate transform where the target is represented in coordinates of the initial position, and that gives you a way of generating the parameters of the movement, which direction, which amplitude of movement you have to do. And there's actually here this generic two-layer architecture that creates some active transient, which is sort of like an oscillator that just does one oscillation, sort of the thing I showed you for the condition of satisfaction dynamics. So this will generate time courses of one-humped activation peaks, which can be used to drive the arm. You can think of those as velocity commands that take you from 0 to peak velocity, go to 0, that would drive the arm to its target. By having a whole field of those, you can determine the amplitude and direction of that movement, and that is actually mapped onto the arm using rate code kind of inverse kinematics to make the arm move, and then the arm's state is computed back to know where the end effector is, and then that's how you predict the end effector position. So there's much more to that. It's a very rough idea of that. So this is the perceptual grounding. This is the motor grounding. And this is actually visual cognition because there's memory here. So there's a whole scene representation. This has memory because it remembers, for instance, where the hand was until you're done. So it's also somewhat cognitive. And up here, that in this system, all that the system has is up here. The cognition consists of a serial order machine, just like I showed, where the ordinal nodes have their memory node, and then excite the next one, and so on. They only again point to colors. That's the same as the Zanemiska system. So they learn colors, and we actually have a learning situation here. This learning node just means when you're in that mode, then certain targets are boosted. They just get some input. While if you're in the recall mode, other units here are boosted. And that essentially switches whether the color you see goes into this field to set up the learning, or whether you generate the color based on what you're currently seeking. So whether you're using this as a percept, driven by a percept, or driven by a memory, and then trying to find that color in the scene. So I want to show you, so here first, this is how it's thought. So here on the top left, you see that you demonstrate the different colors by putting these colors into the visual array of the camera. It's looking down here at this scene. You see here, this is what the camera sees. And you do that in that particular order. So just run it again. So you see first green, then blue, and then pink, and I guess and maybe green again. That's how you teach the system serial order. Again, the timing shouldn't matter, and we're just using the visual transients, the fact that this appears and disappears, to switch the ordinal node so it knows the order. And then we're presenting that system with some scene, like this scene, and we're asking it to essentially move to these different locations in that particular order. So move, put the cursor on top, and this is the end effector, put that on top of the object, blue and then pink, I guess. And I think the fourth is again green, right? If I remember correctly. Yeah. So that's the thing that it learns and performs. And again, the timing of this shouldn't matter. So for instance, it takes longer for the system to make the movement than this presentation time. And you can have objects that are further away, it takes longer to move there. And I'll show you in a moment, you can do online updating. For instance, you can shift something around and it takes longer to reach that target, and that doesn't make the system switch to the next item. It only goes to the next item when it's done with the previous item. So here are some elements from this. So this is how the system learns the timing. Excuse me, not learns the serial order. And so up here you see the ordinal nodes. The green one is the first, the blue is the second, the pink is the third, and this brownish thing is the fourth, and the red line is the condition of satisfaction for this whole ordinal system. So initially the system was started and the first node became active. Actually, by the logic of this, that's what will happen when you boost it and everything is off. So this isn't ready to learn the first system. We're looking at different moments in time, and it's always all this plot refers to the first moment, this second moment in time, but they are not equidistant. So at this moment in time, nothing visible. At this moment in time, the object is presented to the system. It's the only object here, so it easily detects this as a salient object, extracts the color at that location, and the first node is already active. So in this time interval from here to here, the Hebbian learning learns the connections from green for the first node. That's why we use the color green here to illustrate that. It's going to learn green. And these connection weights, as you see here, are illustrated here. They have come to a good value. They are the learned weights for green. And then the green is removed from the scene here at time 2, removed from the scene. We have this offset detector, which detects that. So a peak is being formed here because the system notices that a peak that was at that location is no longer there. And I haven't explained the exact mechanism. It's like a change detector that becomes on transiently as the object disappears. And that is what drives the condition of satisfaction. And the condition of satisfaction inhibits the whole system. You see here, everything goes down as the condition of satisfaction goes up. And then the condition of satisfaction again actually turns off this node and decays by itself, and therefore a release from inhibition will bring the next node up, and the node number 2 by the working memory for first position is the one selected, and now you're ready to learn the next item. And I think it's at this moment in time that you present the next item. See, there can be variable amounts of time. There has to be enough time for the switch to occur. If you show the item before this, the system will not be good at learning it. But after this time, it can anytime now learn an item, and it learns this item, which happens to be blue. And in this interval, while it is in this interval here, it is building the connections to blue. Again, the transient detector picks up that you've removed the blue, and then you'll present the pink. And then actually it has a very long time to learn the pink, and so on. That all works. That's how the learning works. It's very analogous to what Julius and Emiska did. And here is an example of a time course generated with this gradient-based approach. This system is also building a scene representation, like the Grieben system that I showed you when I talked about additional search. So it's whenever it is actually in this mode, the reaching mode, it automatically does that kind of visual search. So it has, I haven't explained the detail in architecture in detail, but also has an intention node, which is an intention to explore the scene visually, and has a condition of satisfaction node. So you see here the intention node is switched off when the condition of satisfaction field is on, and then this is an active transient, so this is some self-terminating, and then an active transient, and so on. And what actually happens is that while the intention node is on, the most salient object, this is the salience map, becomes activated. This is what happens here. The color at that location is extracted. That happens to be pink, like this color here. The system has a working memory, so there is the 3D working memory map. And you see now the system puts into the 3D working memory map that item. It does this by this combining of the color slice, would be this pink color slice, and the location. One of those, I guess it must be this one here, is the peak that's currently being active from this, and that's where a peak forms. There's a bubble here that forms, and that's being entered into working memory. You see later here, this bubble here is the peak in working memory that represents this pink item. It terminates, so you can see you select one item here, and now you have to self-terminate. So when do you stop attending to that? And the notion here is that the condition of satisfaction is when you have entered in working memory the corresponding item. And that's actually done here by this color match field. This color match field gets input from the color that is represented in working memory, which you now extract from working memory, and the color that is currently from the scene. And so when this and that line up, then you're done. So for instance, this can do updating, right? If you have the wrong color at that memory location, something different here now, then it will not match, and it will keep the item in the foreground until the memory has been reset to the correct value. When it's reset, you're saying, oh, I have the right thing at the memory. And of course, if you set it for the first time, this peak will come up exactly when the memory peak comes up, like when this. And it takes a certain amount of time to bring up that peak. It might take longer or less long, depending on how close to threshold you were, maybe how large the salience signal was, or whatever drives the systems through these detection instabilities. And all the while, the intention, the attention selection state stays on. Once this goes up, it inhibits the salience field. You see it's darker blue here. The whole thing is inhibited. As a result, this is inhibited. There is in the background an inhibition of return, which makes that the next time this is not so likely to be activated. I'm not showing that. It can be driven by the same working memory, right? This working memory inhibits that location. And now the system here has, once the inhibition hits, it deletes the peak, which one? The salience peak and the corresponding feature peaks. And as it inhibits that, there is no longer stabilization input to this system, and therefore the system can bring up the next peak. And the next peak here is the next sales item, is the blue one. And now you're extracting the blue color, writing the blue peak here at that location. This is rotated over the top, you see. Extracts blue, there's a match between blue, it gets rid of that, inhibits this, and then the next item would probably be the green, and so on. That's how it sequentially goes through that. So here you see, here it's not a fixed serial order. The order is just dictated by whoever wins this competition for spatial attention. It would be, for instance, this one is selected first because a little bit larger, as you perhaps see. Could be maybe closer to the camera, and that's the most salient one that will be detected first. But so it's just a question, that's what it's gradient based on. It's the amount of input that matters for the serial order. It might not even be reproducible if you do it in different moments in time. It could be a chance selection of one of the other. And then it does things, and the things it does are purely mental, right? There is no perceptual consequence. You see, this picture is always constant here. There's no perceptual consequence of these decisions. It's a purely mental sequence generation. Now, that was underlying that example. And here is the action part. So this is when the system has learned that green is the first color, and I guess blue is the second, and pink the third, and the last one is actually also green, but the color code for the neuron is this brown thing. So it's now being presented with a slightly different scene. And so it's supposed to go to green first because unit 1 is on, and it does that. So it selects the green as a target, and the conditional, so and this drives the arm to that location. The condition of satisfaction for being there is this position match, that is that the system detects that its hand, the end effector, is at the same location as the target position. So this is the input from the target, this is the input from the end effector. Here they don't overlap, and when they overlap, a peak is formed here. That peak inhibits this whole system. Conditional satisfaction drives the conditional satisfaction, which inhibits this whole system, and then the next node comes up, which is activated by its memory, and that's why it's now looking for blue. And then, same thing, when the hand is at the blue, inhibits everything, and then the next item comes up, which happens to be pink, and so on. That's how the sequence generation occurs. So here the times that each act takes are somewhat more similar because these movements are not really so dissimilar, but there's nothing about that that is required. And that's obvious here because this is an example of online updating. So what happens here is that as the arm is moving to blue, so you're trying to get to blue, here it's going to green. Now, at this point, it first moved to green, and then at this point, it switches to trying to get blue. This is here when blue is a target. And as you see, it's trying to move in the direction of blue. It has already selected blue as a target. This is, again, rotated against that. So the blue here is this peak here on the, no, it's, I think, this peak, actually. It's this peak. So this is the green, this is the blue. So from the back, I don't know why it's done that way. And so this is the blue peak. And then the blue object is moved from here to here. The blue object jumps. So it was here and jumps here. And so the target system tracks that and immediately jumps around there. And now that means the movement doesn't reach. So this is updated. The motor system takes this new parameter as it goes, and it will steer the system correctly to the shifted target, property of the movement system. And it terminates only when you are at the blue target. So now this takes longer because of this updating. Here, Ruchin. Now see, this is a longer interval than that, but the system can stay on the blue, and only then, when it has detected overlap, will activate the next color and then moves to the pink, which actually is in quite short now because the pink is a quick little movement. So that shows that this really is able to link, it keeps linking to the sensory information, and so it's able to keep the serial order invariant as the sensory motor details change. That's sort of powerful thing compared to having a fixed program in your mind and extracting a world and acting out the world and so on, updating only at fixed moments as it would be in a classical approach. So with that, I conclude this subunit and summarize by saying that in dynamic field theory, 2 steps are entailed in sequence generation. So one is what the conditional satisfaction captures, namely that you need to deactivate an intentional state. So you're in an intentional state and it has to self-terminate to deactivate. That's based on this mechanism of detection, reverse detection instabilities that create the active transient to deactivate and are triggered by signals from the world or internal signals that match the prediction of what would constitute the condition of satisfaction of that behavior. And then the second aspect is how you select the next thing you do. And there are many different mechanisms for that that are related to each other. I showed you competitive selection in this last example, which is what in the literature was called the gradient approach. It could come from a particular fixed connectivity, the chaining connectivity, and the positional representation is sort of the generalization of that, in which what you chain is just some abstract representation of serial order, and then you point to the correct contents.